Okay, so I will bring this session in English because there are some non-Koreans here. So I'm sorry for the Koreans. And it's 12:30, so I'm gonna start my session here. So, is there anyone who yet to gonna get this link? I'm gonna proceed. Okay then. Hi, so my name is Jen, and I'm working here at DSLV, as I'm writing something like the technical stuffs, and writing some codes, and doing some whatever relation of kind of the Web3 area. So, well, the reason I choose the general knowledge proof stuff is that, well, this is so difficult. Well, honestly, I do not know much about this, but it seems like very interesting stuff. I think that the next big thing in crypto will be on the general knowledge proof. So that drives me to study more. And in this session, I really want you guys to grab something like the basic concept of the TKPs in practical manner, and to have take some interest in getting to learning this, and I'm gonna advertise my study sessions in Boom Labs, which is the crypto developer community in Korea. So yeah, I have this NFT, so I officially represent this one. And so I'm working at this DSLV here. And I started my journey to learn ZK by just thanks to the General Knowledge University, which is provided by the Harmony Protocol. I graduated in the second cohort, and it provided kind of really awesome the educational materials for those who have never ever heard about the general knowledge proof, but to have any kinds of some experiences in writing the contract in Solidity. So before I just started my journey into the Web3, I was kind of the Java Spring, the backend developer. I really love to write some codes in Spring Boot and using kind of JPAs and that kinds of things. I really love that ORM framework, though there's some sophisticated concept on it. And then here in Web3, I'm just exploring the possibility of how the new generation of internet can just blow up the existing the legacy systems. Well, yeah, that's me. So let's proceed. Is there anybody who can define what general knowledge proof is? If you interested in kind of the layer one or the layer two, any kind of bridges, you guys might easy to grab something like the keywords called while we do DK and this DK bridge. Yeah, just freaking great. Yeah, scalability awesome due to this amazing the cryptographic technology. So then, is there anybody here can define what the general proof is? Raise your hand. No? Kyungsa, what is general proof?
I think I can describe it in Korean, but not in English very well.
Okay.
If I try my best,
Mm.
the general rule is that there is two people there, and one person then then something to the other person by some root. And so one person sends the other person something by a certain route, designated route, and person who receives that thing doesn't know about where was the receiving thing. So he or she doesn't know where it comes from. But with a general proof, even though he or she doesn't know where they come from, there is a cryptographic proof that there is only one case where that thing is come from one side. So my English crappy, but this how I understand the general proof.
Yeah, that's right. So, well, to say in concise manner, I think it's kind of the ability to prove an honest computation, yeah, without revealing input, right? So although the fact that input is not the fully concealed to the verifier, the verifier can do kind of the proof by the doing something like the honest computation. So they have these kinds of the magic can happen. So let's kind of take something like the easy example to kind of grasp the example, grasp the idea. So that's a wild example you guys may be heard about. So let's say so well let's find the Waldo in this amazing map, right? So the Alice might can say, I know where the Waldo is, but Alice do not want to reveal the exact location of Waldo, right? So the Bob might ask, well, Alice can be a liar, right? So prove yourself. But Alice do not want to reveal its exact location, but to prove that Alice know where the Waldo is, right? So the Alice can say, yeah, I can prove to you where he is without revealing his location, right? So Alice has two ways to defend her integrity that she knows the location of the Waldo, right? So one, the easy thing is that Alice just could share the Waldo in this piece, and it only shows the Waldo snippet. Yeah, I know the Waldo, so I just crop it. But who Bob, right? So Bob might can say that, wow, you just can just copy the snippet of the Waldo, right? How can I know this? How can you verify that you did not copy of the Waldo? So then, what Alice can do is that to put something like the large opaque sheet of the dashboard, the cardboard, on the top of this scene, right? So the cardboard is much larger than the scene, right? So what Alice can do is to crop from it. What it means is that, well, the Alice can hide the exact location, the XY coordinate. How? Because the cardboard is much larger than the origin scene. By doing that, Alice can easily hide the location. So that is the basic idea of the general proof. So easy, right? So as he said, the coordinates relative to the rest of scene is still unknown. So that's a basic concept of general proof. So what is general proof exactly? We can define the two actors in this process. There is a prover, and the other guy is a verifier. So prover is those who execute the computation, and those who really want to prove to any third party, the verifier, that the prover's computation was valid. Right? And there's verifier. The verifier literally verifies the proof computed from the prover, right? So the verifier's role is just to verify the computation done by someone else was valid, right? So we have the two players here, is prover and the verifier. So how can the prover can make each proof that will be kind of the pass to the verifier in the later process? The prover needs to kind of compute in deterministic way, right? It's a blockchain. So the computation is basically on the deterministic program. So it gets inputs and it returns the outputs. So when it comes to this thing, it's a verifier to verify a computation. The done by a third party was valid would be to run the same program with the same input and check if the output is the same. So which means is that it's a deterministic program. So if you put the same input, the same output will be returned, right? So true is always true. So false is always false. So the prover needs to write the deterministic program called circuit. So that's the responsibility of the prover. So that, as I say, the circuit, that is the deterministic program that prover needs to write. So prover executes the computation on the circuit and the output of the program circuit, right? So the prover itself, starting from the circuit, so they compute the proof, right? What it means is that if you write something like the computation, like deterministic program, circuit, and if you put the certain kind of the proof, which is the declared in the JSON file, you can make your own proof, right? So if you put the input on the circuit, the output, which is a proof, will be returned from the circuit. And you can give this proof to the verifier. So if you say that your input is a private thing, well, there is a kind of combination of the public inputs and private inputs, right? You can designate which kinds of the inputs to be concealed, not to be concealed. So that is kind of things that you can, how can I say, define when you're gonna run the circuit, right? So after that, as I said earlier, you can just compute a proof, okay? So just simple it is to give it to the verifier. So verifier can now run whether the proof is valid or not by just running the contract that is exported in a solidity way. You wrote the circuit and you can compile to the solidity one, and if and the prover might deploy that solidity pile to the Ethereum network, for example. Then the verifier who receives the proof can just put to the contract as a core data, as then just input argument. So then your solidity, the prover's solidity contract will say it's right or wrong. So what I mean is that, well, the prover writes the circuit, and prover kind of computes a proof from the circuit, and the verifier who receives kind of receives the proof from the verifier, received from the prover, can just easily put its code data to the solidity contract, then to easily know whether the proof is valid or not, regardless of to not to know about what the input is exactly it is. So it is to be known that the verifier can just run a kind of lightweight computation. So which means is that the verifier's computation, the resources, is much lighter than that of the prover. The prover needs to kind of compute in more with more energy and more kind of the resources to generate the proof. But the verifier can easily the validate the proof. It's an all one kind of how can I say? Yeah, tasks, right? So in that sense, the verifier does not need to know the whole set of the input, right? So that is the kind of the pro things that the prover can have. So that is kind of the non-interactive knowledge proof, how it works. So we call it as a snark, GK snark. So given a circuit, its inputs, which is private and a public, the prover can run the circuit and generate the proof, as I said earlier, right? So the verifier will run the proof on the circuit, and will know whether it's valid or not, regardless of what the real exact value of the input it is. So the magic of this the generative proof is required to take on these processes. So we are now just running out of time when we just look over into each of the processes. But the whole thing of the conversion logic to the circuit is to give the strict restriction and represent your code into a quadratic form. Which means is that your circuit, your code on generative proof is strictly restricted when you write some code. I will talk in later. So anyhow, in this process, your code will be converted to the quadratic form. Okay. So that is the whole point. So if you really wanted to how the code can be converted into the general knowledge proof kind of circuit, you can just take it into the link to get to know the much deeper on the mathematical concepts. So, yeah, I wrote this kind of the diagram, but it's really difficult to understand. But let me just try to kind of explain this. So, imagine you guys have a task to hash a certain string in 5,000 times in kind of unsolicited contract. It's a literally impossible task, right? If you do so in using the for statement and solidity, it will take the really burdensome the gas fees on the solidity contract, right? So if you really want to do this, you can just pass the responsibility of hash the string on the off chain, and what the on chain contract do is to kind of validate whether the off chain's work is valid or not. So you can just kind of write some contract that can verify whether the hashed string is valid or not. It's in the circuit, which and in the compiled circuit to the solidity contract. Then make your contract to verify to given string is valid or not. That's what the prover needs to do. And write some contracts or the front end that does do kind of the hashing a string responsibility on the off-chain server, for example. And after the off-chain finishes each task, well, just make your front-end code to the verify, or before just proceeding into the next business logic, to the solidity contract. So what I mean is to just pass the output of the off-chain servers, the hash string, to the solidity contract. Then your already deployed provers already deployed contract will say it's valid or not. And after received those the output, you can proceed with the rest of the business logic. So that's some basic idea. If you want to really do something like hash a string 5,000 times, on kind of dealing with within the solidity contract. So if you write your circuit, which is the general knowledge proofs specific the codes, you can just you can just compile it to solidity contract. That's what I mentioned before, right? So that is the verifying contract, right? So literally the contract that verifies the input. Well, if you wrote a circuit and the prover can inject a input, right? For example, you write whether the a multiplied b is 33, and you put the a is kind of 3 and b is 11, right? So, well, it's really easy to compute, but let's say the a is private input and b is the public input. You wanna not to disclose the a as a public input, right? Well, then you can just put the private input a and public input b into in the form of the input.json, and to inject the input.json into the circuit. Then the circuit will create the proving key, which is the specific for your input. Then the proving key can be converted into Solidity's code data, which is available to your verifier's prover's verifying contract, which is already deployed. Then the verifier contract can know whether the proving key is valid or not. Okay, so it's all about the running circuit. Okay, so within this single circuit, the prover needs to deploy the contract that verifier can easily use, and the prover itself needs to put the input not to disclose the ones the private input. So, yeah.
So the problem is you're trying to prove something on solidity,
Mm.
but because doing a lot of computation is hard,
Mm.
you want to do offline computation and just publish the proof on the smart contract,
Yeah.
which let's say a verifier, in our case a node,
Mm.
will take in as an input, try to run through a smart contract.
Mm.
If the contract says, okay, the input is verified, whatever
Yeah,
computation
right.
we try to do
Mm.
is okay,
Mm.
then the data is stored on the blockchain and we continue to do
Yes.
whatever we do.
Yeah.
So, who designs the circuit? Is the circuit the contract, or what exactly is the circuit about?
Well, basically the circuit is written from the designer of the contract, right? So if you're the dApp service provider, want to put this service into a ZK fashioned way, well, the developer of the ZK, they should write the circuit and they deploy the contract before you gonna deploy your own dApp, right?
Hmm.
So
So let's say you have a problem
Yeah.
where you are trying to find out where Waldo is.
yeah,
So now a verifier,
Yeah.
whoever wants to verify whether you found it or not, want to deploy a contract and will convert into circuit and deploy all of the things in the blockchain.
well, you can reuse the already deployed contract.
You can.
Yeah, because well, to find out the Weldo will take the same the mathematical logic. Yeah, if we assume that the kind of the added more kind of jet coordinate from the existing XOI, for example. Yeah. So basically, the service provider will deploy the circuit along with kind of the already in the ordinary Solidity contract. So if you want to write a circuit, as I told earlier, the circuit requires to be represented as some quadratic form, right? So this means that you need another language that puts a strong restriction in a compile level. So the circle language is prevalent to be used in the ZK snarks environment. Okay, so I will talk about what the ZK snarks in later in short time, but we use circum language. So if you write circum language, if you compile with M1CS system, you can have in the WebAssembly file. That a WebAssembly file is a kind of bytecode of your circuit. So you can just generate the verifying key and proving key from your WebAssembly file. Then you can generate your the own Solidity contract to verify the input of the prover from the verifying key.json, which is compiled from the WASM. And that WASM file is originally written from this circuit. Okay. Or that is kind of the general the process of the writing of circuit. Sorry. So for example, you guys know the tornado caches. Yeah, tornado cache is written in the circum language. There's kind of another kind of the alternatives in snarks, like when you say that there's a binary protocol snaps in TypeScript. Well, I originally introduced this session to be write in the Mina protocol, but unfortunately, the Mina protocol's testnet, which is Berkeley QANet, is currently unavailable. So that is why I rolled out that protocol to be used today. So what sad thing is, right? I asked the Discord when to be recovered. They say just they are working on it, but yeah, they just say the Binary protocol's QANet will be back soon. So I don't know. So that is a basic idea. So let's talk about something more deeper. Okay. So so someone would say, yeah, I got your point, but when it comes to in the realistic way, in the pragmatic way, what kinds of library you use, right? So we use snark.js when we do play in the ZK Snark environment. So snark.js, you can just go into the GitHub repository by clicking this link. It's a full-featured tool to generate a proven key and verifying the key from your circuit, right? Circuit from the circuit. So it has kind of full-featured, that is already ready to be the compile the circuit into a WebAssembly file. So it can also generate a smart contract from your WASM file too. Okay. So take a note that Snark.js is well used in the GKP world. So let's talk about how the Snark.js is used. Okay. So this is the journey to create a proof. So if you write something like the in your general knowledge proof stuff in the circle language, you mean that you write circuit. Okay. So the circum has kind of somewhat the different the grammar to that of the Solidity. I think it's somewhat similar to that of Rust a bit, but it has something like kind of some peculiar grammar syntax. So it's much better for you guys to gonna take a look at the getting started in the documentation of Circum 2. It's really well explained. So after you compile the circuit using Snark.js, well, you can have this kinds of the three files. The one is circuit.wasm, which is the WebAssembly file that I mentioned earlier, right? So it is used to generate a witness, okay? So I will talk about what witness is. And the second one is the R1CS, which is represented as a quadratic fashions, but you can just use the WASM, okay? So while there are some developers use R.CS, but when I just look into the something like example, the repositories, the WASM file is prevented to be used. And you can have a circuit.sim, which is makes you gonna debug your kind of circum code, but I will not gonna talk this. So, well, you can make this WASM to be represented in JSON file, okay? So while the compilation, the Snark.js needs to choose which kind of implementation of methods of the Snark.js as CK snarks to be used. So one is the gross 16, okay? So gross 16 is some kind of the things that you require to have a kind of preconditioned thing, which is called the trusted setup. So what is trusted setup? It's let me just put it much simpler, is to put a randomness to your circuit. Why? Because the circuit itself, it should be representative as some kind of the hashed in a hashed version to be encrypted. So you need to put a randomness. But the thing is kind of weird is that the gross 16 requires the two steps of the setting of trusted setup, which means is that you need to do two setups in your trusted setup. So what are two stages of the trusted setup? When it comes to gross 16, regardless of which circuit you write, when you kind of install the Snark.js, you need to install you need to do something like trust setup before and just after the installment of the Snark.js library. But if you do the trust setup in your computer, it will take tons of lots of the times, right? So if you do your trust setup in your computer, I bet you guys do require more than a day in your M1 MacBook. Okay, so initial trust setup is kind of the common one for all guys who uses the Snark.js. So Snark.js is made by the Gcache. You guys have ever heard Gcache is? Yeah, Gcache has kind of its own implementation of Gross 16, and they gonna provide their own implementation of the Gross 16 initial setup, and they provide their own the initial trusted setups file on the GitHub repository. So when you use Snark.js, just not to do your own trust setup, but to just download from on the Gcache GitHub repository. And then if you write the circuit, you need to do another trusted setup, the second step of the trust setup, which is specifically for your own circuit. So the Groth 16 requires the two phases of trusted setup. Compared to that of the Groth 16, the Plonk requires only one trusted setup. So only the initial setup, which is global one, who uses the Plonk system on the Snark.js library, then this whole thing's uploaded. Okay? So you can just download it and just boom. There's no another, the trust setup is required for the specific the circuit. So anyhow, after you put some randomness by doing some trust setup, you can just compile your circuit.wasm into the proving key.json and verification key.json. Okay? So by combining this, you can just have kind of the generated Solidity file. You can just deploy your Solidity file to the ODEN node, which is provided in this, the company. Okay, I just do something advertisement. Okay, so anyhow, you can just deploy Solidity file to the Ethereum network. That is the thing to verify of the prover's input. That is the process of the deploying the verification, the kind of contract. And from the prover side, if the responsibility of prover is to make your own proof itself, right? To just not to disclose your private inputs, right? So, well, the prover itself is the user of the dApp, right? User might want to not to disclose your the user's input. This means is that user can choose which input to be disclosed and which input to be not to be disclosed. So you can just put your input.json, let's say the A3, B11, that's the example that I already mentioned before. You put your input.json into the circuit.wasm. Yes, the circuit.wasm is recorded by both the guys who write the contract and do something like provide the service, and from the prover side, which means is that if you're the front end of a decentralized application wants to make a proof for the user, your the React application, for example, needs to be deployed in any kinds of the server or first set or app, any kinds of static website with the circuit.wasm. Yeah, so it needs to be deployed with the WebAssembly file. So the user's the input to be represented in the JSON file, and the React website to be injected with the input.json. Okay, so the circuit.wasm on the front end website to calculate the witness. Okay, what is witness? Witness is all the possibilities of A and B, of the combination of A and B. So when you put the A is 3 and B is 11, well, we don't know which is A and which is B, but it just says, oh, the multiplication of 3 and 11 is 33. Well, boom, right, 33. But it could be 1 to 11, right? So that's 11. It could be 3 and 1 is 3, and yeah. So there's all the possibilities of the combination of the results and that is the witness.json. Okay. Then the witness.json to generate the proof. So we finally have the two files. The one is the public.json to disclose the user's input as a public one. Then you can have your proof.json, which is the encrypted the input of the public one and the private one. That's a combination of the whole input. And you can just generate it as a proof.json. So the front end side will finally get the proof.json and the public.json. That is the side of the prover, and that is the side of the front end for the flow of the user. So the thing is, how can we make these two kinds of the JSON files to be injected on the Solidity contract, which is verifiers 1, right? So let's talk about the verifier side. the asset from of the provider side on the front-end code is to have the two JSON, as I told earlier. Then this proof.json and public.json should be represented as a verification key.json, which is kind of distinct one from that of the verification key.json in the previous slides. So you can just compile your verification key.json using the Snark.js library, which means is that your front-end application should have its dependency to the Snark.js library. And if you gonna, if the user, for example, clicks the submit button, for example, then the Snark.js library comes into here and to gonna compile your proof.json and purport.json to be on the verification key.json, okay? So, well, the Snark.js can itself to verify whether your verification key.json is valid or not. If your Snark.js have the WASM file, okay? But the thing is, your verification should be done on the on-chain to be transparently do the computation on the Ethereum's global machine, right? So what we wanna do is to make the proof.json and the public.json to be converted with these kinds of the weird arrays. This to be on the core data to be injected in the Solidity contract to verification contract, okay? So if you put this the core data into this A, B, C input, which is just defined in the verification contract, then if you proceed with the doing some call, the verify proof function, it will return whether it's valid or not. Your proof is valid or not. So that's the general way of how this kind of contract works. Okay. So simply put, user A, which is front-end side, generates a proof locally on the front end with a WebAssembly file in the Node.js application or the React application or whatever. That submits a proof to the smart contract, and smart contract, the verify proof method will say whether the proof is valid or not. Okay, so that's a general idea. So I just said about the trusted setups and parts of toe. We often use this growth 16 when we compile the WASM file into the proving key.json. The growth 16 is some general gold standard in the GKP world in 2022. It has kind of very efficient proof time and constant proof size, while it has something like the relatively fast verification time to compare to the competitors. And it has lots of tools like the Circumlab, the Snark.js. It's very easy to use. However, as I said earlier, the growth 16 requires two phases of trust setups. One is for the global setup, and second is for the specific circuits. But as I said earlier, the global setup is not required to run by your own machine, but you can just download, which is already done from the GKC Foundation, which is already public to the GitHub repository. So if you really want to get to know much deeper, so take out these links. Okay. So there's alternatives, as I told earlier. That's a Plonk, right? That's a universal trust setup. It does not require another setup for specific circuit, but it's lower than growth 16. And the curve proof size is bigger, verification time is slower, and tools is now evolving, and they are now just working in progress. So the Alzect and Mina and the Mir is working on the Plonk, okay? So this is kind of is some existing example of the ZKP in Ethereum network. So Tornado Cache is really the well-known to want to hide your transaction, the recipient, and the balance. And there's a Dark Forest, which is MMORPG game, which is represented with the first MMORPG game deployed on the Ethereum contract with the power of the ZK Snarks. So if you play this game, you can just secretly that opens your arsenal to the other game players without the right exact location on the blockchain site. So that's so fun. So if you are interested, so take this dark forest. Yeah, if you want to really join on the game, you gonna put something like stable coins there, and the winner of the game will take some stable coins. That's a basic logic of the game. And there's some examples here. There's a GK photo. What is GK photo is? The GK photo is to upload a low resolution image which is converted from the high resolution image. What I mean is that if you want to sell your high resolution image 4K photos that depict this Gangnam landscape, if you want to sell that 4K image, well, let's say you upload the 4K image to the OpenSea. Well, someone can just simply download the image from the website, right? However, you want to just prove that you have a high resolution image, but not to let's say upload the link of the 4K image, or just upload the 4K image to the IPFS, not to disclose your own image, but to just upload a low resolution image with the mathematical proof, DK version proof, that you had already converted your high resolution image to the low resolution image. That would be proof that you have a high resolution image without disclosing it, right? So that's a really amazing project. This project is done by the Hong Kong University professor in cryptography. So I do not know how this works exactly, because the code is really difficult, but it's really an interesting project. And my one is the ZK identity, which is a graduation project from the General Knowledge University. I have this video here, so let's take this. So this is the concept that comes from the dark forest. Dark forest consists of the 5 rounds for each game. But each game, for the sake of the enjoyment of the game, the 33% from the bottom to be rolled out on the next stage. Then the rest of the game players should not disclose who is the first stage or who is the fifth stage. So they need to not to disclose the exact rank of their previous stage. So that that brings more enjoyment to the game. So how can we achieve this? So I gonna do this in a clone coding. So if you have the designated of the winner of the game, the contract already knows, this is hard-coded in the GitHub repository, that who is the winner of this. Then the winner can claim NFT anonymously to another address, which means is that you can verify that you are the winner of the existing address. Then you can mint your NFT to the different EOA address. So that kind of the ZK project is I just submitted this graduate project to the ZKU. So let's see. So you can claim your own reward by connecting your wallet. Okay. We gonna use this address to connect the wallet. This address is the winner. Okay. So contract knows this contract is in the winner, and this the list of the winner is represented as a Merkle-tree's root. So the third party cannot know easily. And if you verify yourself as the winner, the front end might create a proof. Okay. So you can just copy your proof and you can claim to the address that you want to gonna claim your NFT to a specific address. Okay, so put your the proof here, and to put you're the recipient of the NFT that represented you were the winner of the previous round to here. Then you can anonymously to claim to address without needing to disclose the recipient of address to the blockchain. Okay, you can just hide the recipient on the public blockchain. Yeah, and transaction has sent, and you can check the transaction here. Okay. So the key of this is to hide the recipient. Okay. Though it was a public blockchain, you can just hide the recipient. That's a measure of GK. Okay. So, well, I have this simple example, but we are just running out of time. I'm gonna just skip this. So, Interrupt is the service that to prove that you are, for example, you have more than 5,000 commits to date, without letting you know which GitHub repository that you are. Okay. So this can be used to be on the Web3 social network to hide your own identity while proving that you are in a certain condition. Okay. So it's on the Interrupt link. So it's really easy to use. So yeah, take this. Okay. It's a good example. So the moonshot, some ideas that the the general knowledge proof application can be used. Okay. Is based on the scalability and the privacy. So what kinds of ideas can be derived from the zero knowledge proof? Like the secret data marketplaces, as I told earlier in the GK photo project. Okay, decentralized machine learning oracles. Okay, so you might not to disclose the certain your personal data to the Facebook, for example, but to say, yeah, I love to shopping the Apple products, but I do not want to disclose that I have bought my MacBook Pro in 30 times, for example, right? So you can just do that. And take this, the Substack.com, and he is kind of the leader of the 0xPIRC, which is a working group for the writing some general knowledge proof applications that develops the Snort.js and Sarcom. So take this Substack for getting more ideas of the GKP, okay? So what is too long but don't read? So Snarks is the gold standard for writing general knowledge proof for existing just ordinary Solidity developers. Like with any proof systems, there's a prover, verifier, and a challenge, which is a proof, okay? So to make challenge non-interactive, which is not to interact before the verification, there is some hard-coded common reference string that is the randomness, okay? So randomness, which is set up during the trusted setup, okay? And the random string is encrypted to be reused, and it is really important for those who inject the random string to hide their string, okay? Not to just to recompute it's the proof to make the verifier to say the certain proof is valid, which is not valid. So the Zcash literally creates this initial phase setup with the kind of 100 of partakers to put each one of them on different string, then concatenate that string and put it as a randomness. And Zcash has made the transparent on the proof that each of the participants of the initial phase setup to literally burn the string of what they have input. Okay. So that's what the Gcash says while we are decentralized. Why? Because we prove that each of the participants already deleted a string from their own machine. And well, they try to kind of prove that. But this means is that we have something like kind of the single point of the failure. If someone can just lie, right, by just manipulating their mathematical proof, if they're possible to do so. So that's why some guys are really, the developers are really looking forward to the implementation, the practical implementation of the Plonk or the Starks, which does not need or which requires only one initial trusted setup. So the initial setup is really key point to keep the ZK to be on ZK. Okay. So there are some cool tools for the zero knowledge proof, writing your own application. One is the semaphore protocol, which tries to wrap your Circum library into a TypeScript one, which is along with the ZK kit. They try to wrap your Circum library into a TypeScript or JavaScript. But this means that it lacks something like features. You cannot use your full features of the Circum, but which means is that you can just easily implement this zero knowledge proof idea into your application. And the Mina protocol, which just suspends its testnet, I don't know. And allow, which tries to be on another layer one that's specifically designed for the general knowledge proof. And Stockwell which is really famous. I want to mention it. Okay. So let's do some quick tutorial. So you can just clone your repository on here, the sample ZK app. I already tried to write the ZK Sudoku, which means is that the players can submit your own answer without revealing to the public blockchain, to Ethereum blockchain. So the other third parties, like for other game players, cannot know which answer was submitted from the submitter, right? So the Vivian, she was my colleague on General University. They wrote the initial idea of the Sudoku, so I really thank her. And you can take the basic website here, sample zk-sudoku.versa.app, okay? So let's play a little bit, okay? So connect the wallet. It's boom, okay? So let's play Sudoku, okay? Well, I'm not good at Sudoku, so I'll type something like arbitrary one. So it's empty one, so 8. So let's verify Sudoku. Oh, wrong solution, okay? Wrong solution, okay? So that's a ZK Sudoku basically made with. So take your repository here and clone it. I'm gonna shortly describe how this code is written. Okay. So let's talk about Circum. Okay. Circum is all about the kind of restaurant. Okay. It's all about the kind of putting a strong restriction on writing your own variables. What I have already mentioned is that the circuits should be written in a quadratic form, which means is that if you write in a linear form or more than more than a quadratic form, the compiler will reject your code. Okay. So you can easily take your code on the web IDE, like the Remix one in Ethereum, on the zk rdpl.dev. Okay. So you can easily test and compile the Circum code on here, okay? So this one. Let's talk about a little bit. This is a quadratic form, okay? A multiply B. Then it puts the variable, the output to C. Okay. When you write in this way, this means is to gonna assign the output of A multiply B to the new variable C. But it does not mean which is not equal character here, just a single line here. It's just to assign parameter, not to verify whether the C should be A multiply B. So the reason why we write circum is to verify one, to put a strong restriction on the variable. So you need to do, and this way, that's a common way. Okay. So A multiply B should be a variable C, and this will be strong restriction. So let's compile it anyhow. It compiled one with R1CS and SIOM and main Dawson. So you will need to play with this main Dawson. But let's say, let's do some like the triple form, okay? Like the okay. So does it possible to multiply A, B, and D? The answer is no, right? It only accepts the quadratic form. So let's say we have A, B, and D as the input. If you say A is serial input, that's a public one. You can put this as a private, okay? So anyhow, let's say A multiply B multiply D can be a variable C. When you compile this, it returns that the constraint with the non-quadratic form is allowed. So how can we make this? How can you assign variable with multiplying A, B, and D to represent this one in a quadratic form? That's really difficult, sophisticated. That's why we say, oh, the writing GK circuit and writing the general knowledge proof, something like it's really difficult to implement in the existing protocol. That's why in this way. That's why this the reason. To represent your code just simply on a quadratic way is really difficult. So I just put some tweet that how can I make it. So let's take this one. Yeah, here is a simple circuit made with circumlab. I will just enlarge this website screen. Okay, so let's say we have a basic template that allows you to check if a given number is there or not. So there's an in, there's an out. Let's say this trinary operator can be assigned to IMV. Okay. Well, as I said, this equals character with on this form is not one, right? It's just a line single, right? This means is that we do not give restriction on IMV, just the assignment of the output of this one. But the out is to the burdened with the constraints that should be on quadratic form, okay? And anyhow, you wanna do is that, well, your input in is general not, and the output is to say, well, your one is general not, okay? But it will not work because of the trinary operator. Trinary operator is not allowed in the circle way because it's not represented in which way? Quadratic form, okay? So you might believe that this ternary operator to compare whether the number is zero or not seems to be a simple way, but compared throws an error. Why? Because the constraint needs to be quadratic, and constraints can only have the quadratic form. So how can you make it? Is on where it is? Isn't here. Okay. So this was the answer. This was the answer. The wrong thing was here. Okay. I was kind of mistake. The wrong thing was here. Oh, the input was in. Is there or not? It is not. Yeah, right in the kind of the quadratic format. But the correct answer is this one, because IMV does not have its constraints to be on quadratic form, but out, which is an output of the circuit, is written in the quadratic form way. How we make this? Because we inverse the input of the public. Okay, so we inverse the input so that we can just multiply the original one version, then the inverse version, to make it as some quadratic form. So that's a trick, that's a mimic. But you need to do this if you want to use the circum language, which is claimed to be a gold standard of the Zen-Ulrich proof. So how can I turn it off? Where's my mouse? Okay. So let's back to the slide. That's the way why we say the circum is difficult, because of the restriction of the zk-SNARS implementation. So anyhow, let's take the example of the zk Sudoku. We will not go into the deeper of this code because of the short of time, but let's do our own test. So I will give a kind of, you guys have already the cloned repository or to put your own ID. So this one is for. Let me do something like the adjustment of our the font size. So clone the repository. Oh shit. Is it okay? Right? Let's see. It's difficult to wanna read this one in the left side, so. How can I do this? Okay then. Yeah. Here. So we have Stochasm, which is compiled from the circuit here. There's a Sudoku circuit here in Stochasm circle. So that is the code that verifies the user's input. Well, let's make this circum file anyhow to compile, okay? So let's compile this. I have a file that compiles automatically with using the shell script. It's a compile.sh. It's a simple one. Just compile the circuit with the circum command. So let's do like compile.sh. The shell script writes the R1CS, SRM, and the Watson file. Okay. So let's put some input file. We have input file here. Okay. So to be on the prover side, let's put this input to the wasm file to generate a proof. So this one is solved one, which is an answer, and this one is to be submitted answer to not to be disclosed on the public blockchain. So we have input.json, then we can generate the witness. Generate the witness file is here. Okay. So we have the generated witness.js, which is automatically generated from the circumlib after you compile the circuit. So if you run generate witness.sh, I just forgot how can I just give them permission. So you plus something. Okay, so then so we generate the witness, okay? It creates the witness. Then you can just download your Go16 file by running in this shell script. You download initial the trusted setup from this link. Okay, this link is provided from the Jetcache. Then it compiles circuit again and does witness.wtns, which is we done already. It's the same logic. Then it generate that key file, and we put the second ceremony, which is specific for the circuit. We put some random text here. So it's not a thing for a practical kind of the production level, because if you really want to gonna do in a production level, you need to decentralize the way of putting the random text. Okay. So the export the verification key, then generates the DK proof and verified proof, and generate the solid verifier, which to be deployed in the solid contract. Then the print parameters of the call. So we gonna the input the output of the generate call function method on the verifier.sol, which can be say is valid or not. Okay. So let's run. Then execute. I already have the file of the initial setup, but the download takes a lot of time. And you can see that the generation of the ZK file, which is to be proof, is really slow. So as I mentioned earlier, the prover takes some computation time, while verifier can do the computation with all one fashion. Yeah. You can just put this this kind of the writing the code data to the solid contract. So we can just test the circuit also. We have a test in which files to be? Here maybe, yeah. It's a test of the verifying contract. So the verifying contract might return true for the valid proof on-chain. And from the front-end side, this is the front-end side test code. So it has WASM file and ZK file. And after inject that, you can have the output of the verified proof. Okay. So take a look at this testing function, how it works. So let me just show whether it works well or not. let's npm test. It passes, right? So it did this. The test function verifies whether the verified contract work well or not in the front-end side. So this kinds of the way to generate a code data to be put on the Solidity contract is generated from this unsolved and solved array by just running this code export code data pro 16, which is declared in the snark.js, which is to be a dependency of the front-end code. Then the verified proof, which is to be deployed in the local blockchain. Then it returns valid or not. So, well, we just have running out of time, so I will just skip the rest of the explanation of this. But I think that this kind of example is really great to understand this DK implementation in the front-end side and for the prover side. So, well, I'm also learning the DK one. So it's really interesting for me. It's really difficult to grasp, and I do not fully understand of this, but it's really interesting from my side. Okay, so that's what I told earlier. Okay, that's on the test side. So I want to recommend something materials to study more. Is that, well, first of all, the ZKU study session is really amazing. So there would be the another cohort starting from the September. So take a look. And the General X Park, PARC, which is working group of the general knowledge proof, which develops snark.js. They really do amazing thing, and they wanna do something like the offline conference in Silicon Valley in September. So take a look. And the General Knowledge podcast and GK Hub provides regularly a really amazing materials for it. And you can take something like the awesome General Knowledge Proof GitHub repository that provides you a full example to get into it. And I'm currently operating something like study session on General Knowledge Proof, writing something examples with snark.js and Sarcom, and we now do we're now following the documentation of Sarcom right now in the Boom Labs. Boom Labs is a crypto developer community in Korea, and we have the ZK EVM's basics contract session and ZK session and Solana session also. So we are trying to be on the developer DAO that brings the Web2 developers to the bridge into the Web3 and to find their own colleague to do your own business or to find colleagues to go into a hackathon, for example. So we try to be the crypto community, developer community in Korea, and to expand global in afterwards. So if you're really interested in studying more with me or our colleagues, so take the link of this Discord to join the Boom Labs. Okay, so take a look. It's really amazing. Guys are maintaining our community. So I'm really thank you to be on the final session of the DSLV Builders House. So I really thank you very much to take the session. Thank you.